Welcome to Math with EJD. In this video, we are talking about numerical differentiation using difference operators. I made a previous video introducing us to the difference operators like forward difference, backward difference, central difference, and we saw that central difference is the most accurate of the three. Then, of course, talking about relationships between all the operators, we introduced the idea of shift operator, which helps to connect all these operators together. So here, I want to take actual examples to make us understand the use of those operators in solving problems. So we start straight up with forward difference operator. Forward difference operator with this triangle facing up sign. So imagine that you're given the function f of x equals x squared. So using the forward difference formula, so using this formula now, you see that you need df of x, that's f of x plus h minus f of x. Then the second difference is d squared f of x, which is equal to d of f of x, and that is the same as, so that tells you that d squared f of x actually is the same as f of x plus 2h minus 2f x plus h plus f of x. So with that settled, so imagine that you have x to be equal to 1 and h is also equal to 1. So you can see this. We need f of x, we need f of x plus h, we need f of x plus 2h. So that means that f of x is the same thing as f of 1, which is equal to 1 squared, because the function itself is f of x equals x squared. So we have 1 squared, and that is 1. Then we need f of x plus h, which is f of 1 plus 1, and that is f of 2. That means you have 2 squared, and that is 4. Then we need f of x plus 2h, and that is equal to f of 1 plus 2 into 1. That is equal to f of 1 plus 2, that is f of 3, which is 3 squared, and that is equal to 9, like that. So with all of that in place, then we can talk about the differences. Imagine the first forward difference, So the first forward difference will be things like delta f of 1, which is, and delta f of 1 is basically f of 1 plus 1. Of course, you know what delta is. That's x plus h, right? Minus f of 1 itself. So, and that would be f of 2 minus f of 1. And that is equal to 4 minus 1 equals 3, like we have up there. So delta f of 1 is basically 3 already. Then you have delta, the second first forward difference will now be delta f of 2. So that is f of 2 plus 1, of course, minus f of 2 itself. Okay. So it means that x9 is like our 2 here. So we have f of 3 minus f of 2. So f of 3 from what we got up there is 9. So that is 9. Okay, I can bring that down because we need space. So that's 9 minus f of 2 is 4. And that is equal to 5. So that is the second first forward difference. So in essence, we're saying that df of 2 is equal to 5. So taking that further, we now need the second forward difference. So the second forward difference will just be delta squared f of 1, and that is delta f of 2 minus delta f of 1. So delta f of 2, we already got that to be 5. Delta f of 1, we got that to be 3. So that tells us that delta squared f of 1 is equal to 2. So this is important. And what does that teach us? This confirms that the second order finite difference of f of x equals x squared is constant. It confirms that it's constant, matching f prime prime of x equals 2. And really, if you see this, f prime of x is 2x, f prime prime of x is just 2, and that becomes the constant value that holds. Now, let's go on to the backward difference operator. Backward difference operator with the sign, with the symbol nabla. Okay, so now nabla, given f of x equals x cubed, using backward difference formula, okay, so we have nabla f of x equals f of x minus f of x minus h. Okay, so if we take for x equals 2 now, we have nabla f of 2 is simply nabla f of 2 will simply be f of 2 minus f of 2 minus 1. That's assuming that h is equal to 1. Okay, so then we have nabla f of 2 to be f of 2 minus f of 1. So the function we have is x cubed. Okay, function is x cubed. So nabla f of 2 is equal to 2 raised to power 3 minus 1 raised to power 3. So nabla f2 is equal to 8 minus 1. So that finally we have nabla f of 2 to be equal to 7, like that. So then we go ahead and talk about we now have the central difference operator delta, central difference operator delta. So in this case, imagine that we are given f of x equals sine x. Okay, so the central difference formula is delta f of x, which is equal to f of x plus h minus f of x minus h. Normally the central difference itself actually tells us that f prime of x is equal to, okay, maybe I should just, let me speak to that. So normally, that f prime of x is equal to f of x plus h minus f of x minus h divided by 2h. So if you go with that, it simply means that we have 2h f prime of x to be equal to f of x plus h minus f of x minus h. So this whole thing now is what becomes your central difference operator. So that's the f of x, equals f of x plus h minus f of x minus h. So in other terms, we are saying that delta f of x is approximately 2h f prime of x, which implies that f prime of x is approximately delta f of x divided by 2 time steps, basically. So, but then that's by the way. If we go on with what we have, so if we say for x equals pi over 4, for x equals pi over 4, and h equals 0.1. See what we get? We have f of pi over 4 plus 0.1. That will be equal to sine. Now, if you add this together, that's actually 0.8854, and that is approximately 0.774. Then you have f of pi over 4 minus 1. That is equal to sine 0.6854, which is approximately 0.632. So if that is the case, then you can come back to say that the central difference, f of x, is equal to, of course, we know what that is normally. That is f of pi over 4 plus 0.1 minus f of pi over 4 minus 0.1. So that means that the central difference of f of x is actually equal to 0.774 minus 0.632. So that means that df of x is equal to 0.142, like that. Then we can also estimate the derivative, right? From here, we know that f prime of x is approximately dfx over 2h. So now we say also f prime of x is approximately central difference of f of x divided by 2h, and that means that f prime of x is approximately the central difference we just get is 0.142 divided by 2 times 0.1, and that is equal to 0.142 divided by 0.2. That is the same thing as 0.71. So you see now that f prime of x is equal to 0.71. Does that look like something we can verify? Let's see. The true derivative, actually, the true derivative of the true derivative of f of x, which is equal to sine x, is f prime of x equals cos x. So at x equals pi over 4, pi over 4 rad is like it's like 45 degrees, I believe. Yeah, that's 45 degrees. Pi over 4 rad is 45 degrees. So at x equals pi over 4, we have f of x, which is equal to, okay, let me take it down. We have f of x, which is equal to f of pi over 4, which is the same thing as sine of pi over 4, to be equal to root 2 over 2. Root 2 over 2, and that is so we say that f of x, which is root 2 over 2, is approximately 0.7071, actually 0.7071. So I mean, to 2 decimal places, it's almost there, right? 0.7071 is like 0.71. So confirming, so this actually confirming the accuracy of the central difference method. Okay, so with that now, let's move on to, I guess, the last part of this now. So talking about, so for number 4, we have relationship. between operators. Relationship between operators. Imagine that you need to verify that the forward difference of f of x is equal to the shift operator multiplied by the backward difference of f of x for f of x equals x squared at x equals 2 with h equals 1. So for the solution, we first compute the backward difference of f of 2. So that is the backward difference of f of 2 would simply be f of 2 minus f of 1 by the very definition of backward difference. So that means we have 2 squared minus 1 squared. That is equal to 4 minus 1. So that is 3. Therefore, the backward difference of f of 2 is equal to 3. So that goes. So the next thing we want to do is to apply the shift operator E, the shift operator E, which shifts function values forward. So we're applying that to the backward difference now. So that means we have the shift operator together with the backward difference of f of x, and that will just give us the backward difference of f of x. So because it's shifting it forward, so we now have the backward difference of f of x plus h. So h moves a step ahead. That's what the shift operator does. So as a result of that, instead of shift 2 now, instead of backward difference of 2, we move to the backward difference of 3. Okay, so the backward difference of 3, the backward difference of the function of 3 is equal to f of 3 minus f of 2. So that is 3 squared minus 2 squared. That is 9 minus 4, and that is 5. So again, we have the backward difference of f of 3 to be equal to 5. We have that. Then we move on. So we see that since the forward difference of f of 2, so in the case of forward difference now, we have that'll be f of 2 plus 1, because 1 is h, right? Minus f of 2 itself. So that is f of 3 minus f of 2. So again, f of 3 is 3 squared. F of 2 is 2 squared. That is 9 minus 4. And that is also 5. Okay. So before we even talk about the since part of it, let's now say that so forward difference of f of 2 is 5 again. So since the forward difference of f of 2 is equal to 5, we verify that the forward difference of f of 2 is the same thing as the shift operator together with the backward difference of f of 2, and all of that is equal to 5. Thus, the relationship holds. The relationship holds. So in conclusion, these examples demonstrate how finite difference operators approximate derivatives and how they relate to each other in numerical differentiation. So in the next video, I'll start with numerical integration, talking about trapezoidal rule, I think. If you have subscribed, thank you for that. If you have not, please go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Then comment. Let me know how helpful this video is, and let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to this great content, because I have so much more coming your way. So before then, keep doing math right. Bye.